All right, let's dive right in, folks. Into the quantum abyss. Ready to have your minds bent a little?
Always up for a good mind bending.
Today's deep dive is all about quantum mechanics. Specifically, we're tackling Schrödinger's cat,
Classic.
superposition, and entanglement. We've got a stack of academic papers and some textbook excerpts to guide us.
Sounds dense.
It is, but fascinating. So get ready to explore a world where cats can be both alive and dead.
The joys of superposition.
And particles are, well, kind of spooky.
Spooky action at a distance. Isn't that what Einstein called it?
He did. But before we get to the spooky stuff, let's start with everyone's favorite feline thought experiment, Schrödinger's cat. More than just a thought experiment, though, right?
Oh, absolutely. Schrödinger's cat stuck in a box with a lethal contraption was meant to highlight how absurd it seemed to apply quantum principles to everyday objects. The idea is that until we open the box, the cat exists in a superposition of states, both alive and dead at the same time.
We haven't actually superposed any cats yet, have we?
Not that I'm aware of, but the real surprise is that recent experiments have shown superpositioning happening in larger systems than we ever thought possible.
Like, how large are we talking?
Not cat-sized yet, but bigger than a single atom, that's for sure.
Yeah.
The line between the quantum world and our classical world, the one we experience every day, it's blurring.
So this isn't just us not knowing, like, whether the coin landed heads or tails. Things really are in multiple states at once.
That's the mind-blowing part. It's what superposition is all about. Imagine a single particle, the tiniest building block of matter.
Got it.
Before we measure it, it doesn't have a definite position, momentum, or spin. It exists as this blurry cloud of possibilities.
Like a wave function spread out over space. I've seen that in the papers.
Exactly. Only when we measure it does it collapse into a definite state, like our coin finally landing on heads or tails.
Ah. Okay, so that's where the whole both alive and dead cat comes in.
Right.
It's in this superposition of states until someone or something takes a peek inside the box.
Precisely. Now, scaling that up to a cat is, well, still in the realm of thought experiments.
We're not going to be playing quantum roulette with real cats anytime soon, are we?
Hopefully not. But the principle is the same. And here's where it gets even wilder.
Wilder than a cat being both alive and dead. Okay, I'm listening.
This isn't just some theoretical quirk. This idea of superposition, it's actually being used to build quantum computers.
Wait, quantum computers. Can we hold off on that for a sec?
Sure.
Before we get there, I want to make sure I understand this whole collapsing into a definite state thing. Does that mean we're somehow creating reality by observing it?
That's the million-dollar question, and it takes us right to the heart of the mystery of quantum mechanics.
Totally.
Before we dive into the whole role of observation thing, we need to kind of wrap our heads around this idea of probability amplitudes.
Okay, so walk me through it. What are probability amplitudes?
Okay.
And how do they work?
So imagine like a quantum particle, like an electron. Instead of existing in a definite state, it exists in a haze of possibilities.
Okay.
A blend of all possible states, each with a certain probability of becoming real. These probabilities are determined by something called a probability amplitude.
So instead of a particle having like one definite location,
Right.
it's like it's spread out across multiple locations at the same time.
Exactly. And each of those potential locations
Yeah.
has a certain probability amplitude associated with it.
I see.
It's not that we just don't know where the particle is. It's that its location isn't fixed until we measure it.
Okay.
It's kind of like the particle is exploring all its options simultaneously.
Okay, so how does observation come into play? How does
Yeah.
a blurry haze of possibilities collapse into a definite outcome?
That's where things get really interesting.
Okay.
And where the debate about the role of consciousness really heats up.
Oh, yeah.
When we observe a quantum system,
Yeah.
we kind of force it to choose one of these possible outcomes.
Okay.
The very act of measurement seems to collapse the wave function, the mathematical description of the particle's state,
Right.
from a superposition of possibilities into a single reality.
So if I understand correctly, before we look it up, the particle is potentially everywhere at once,
Yeah,
and then boom, the moment we observe it,
right.
it snaps into a definite location.
That's the essence of it.
Okay.
And it raises the question, what role does the observer, potentially even consciousness, play in this collapse?
Right.
Are we, in some sense, creating reality by observing it?
It's a mind-boggling concept.
It is.
Yeah, I mean, if our consciousness is what collapses the wave function,
Right.
does that mean reality doesn't exist until we observe it?
Well,
Are we living in some kind of mind-created simulation?
there's no single agreed-upon answer.
Right.
And that's what makes this whole discussion so fascinating.
Yeah.
Some physicists, like Roger Penrose,
Okay.
believe that consciousness might be deeply connected to the quantum world
Okay.
and plays a fundamental role in collapsing the wave function.
So they're saying that, like, our minds are somehow shaping reality at the quantum level.
It's a controversial idea, but it's a possibility that's being seriously considered.
Okay. So some physicists think consciousness is the key.
Right.
But what did the skeptics say?
A lot of physicists argue that consciousness is simply another physical process interacting with quantum systems,
Okay.
not some special force that transcends physics.
Right.
They believe the collapse can be explained entirely within the framework of existing physical laws.
So instead of our minds shaping reality,
Right.
the measuring device interacts with the particle.
Right.
That interaction causes another interaction.
Exactly.
And so on until eventually we get a definite outcome.
And this brings us to another intriguing possibility.
Okay.
What if our tools,
Yeah.
the very instruments we use to observe these particles,
Right.
are just too crude?
You mean like we're trying to study a delicate butterfly with a sledgehammer?
Exactly.
Yeah.
Maybe our attempts to measure these particles are so intrusive that we're creating the very changes we're attributing to observation.
Right.
It's like trying to measure the size of a soap bubble by poking it with a needle.
Right.
You're bound to change its shape, right?
So what we see as the collapse of the wave function
Yeah.
could just be the result of our clumsy tools interfering with the delicate quantum world.
It could be.
That's a humbling thought.
It is. It's a question that, really pushes us to the edge of what we know and what we think about reality.
Totally.
We're used to a world where things just are.
Right.
But, quantum mechanics suggests that
Yeah.
at the most fundamental level, things might only become real when we observe them.
So we've got a stack of fascinating research here.
Yeah.
Articles from Harvard and Oxford, experimental data, some of my own notes.
Oh.
And our mission is to unpack this mind-bending idea.
Okay. There's the Copenhagen interpretation.
I've heard of that one.
It says that observing a system forces it to choose a state.
So even the act of looking at the quantum world changes it. That's a pretty heavy concept.
It is. And it leads us to another fascinating concept, Heisenberg's uncertainty principle. And this uncertainty comes directly from the wave-like nature of particles. Imagine a wave on the ocean. It's spread out, not at a single point.
Okay.
The more we try to pin down its position, the less certain we are about its wavelength.
Just measurement error, right?
I always think about it like, imagine trying to pinpoint the exact location of a tiny particle.
Yeah.
To do that, you need to shine some light on it. The act of shining light,
Okay.
interacting with that particle, inevitably changes its momentum.
Got it.
And the more precisely you try to measure its position, the more you disrupt its momentum.
Right.
It's like trying to catch a feather in a hurricane.
Oh, wow.
Your very attempt to grab it sends it flying off in a different direction.
Okay, so it's not just about our clumsy tools.
Right.
It's a fundamental limit
Yeah.
built into the fabric of reality.
Exactly. The Harvard article highlighted this beautifully.
Oh, cool.
It pointed out that to measure a particle's position with more accuracy,
Right.
you need light with a shorter wavelength,
Okay.
like using a finer tipped needle to examine something delicate.
I see.
But shorter wavelengths pack more energy.
Right.
Think of the difference between a gentle wave and a crashing tsunami. When that high energy light hits the particle,
Right.
it transfers more momentum, making the particle's momentum even more uncertain.
So there's this inherent trade-off. The more you know about where something is,
Right.
the less you know about where it's going and vice versa.
And that, in a nutshell, is the uncertainty principle.
Okay.
It tells us that at the quantum level, reality is inherently blurry.
Wow.
It only snaps into focus when we observe it.
Okay, that's already pretty wild.
Yeah.
But then things get even weirder with this idea of entanglement.
Oh, yeah. Entanglement is one of the most baffling phenomena in quantum mechanics. It's the idea that two particles can become linked even across vast distances.
Okay.
So that measuring the state of one instantly affects the state of the other.
So it's like they're communicating faster than the speed of light.
That's the part that really bothered Einstein, and I can't blame him.
Yeah.
He called it spooky action at a distance and believed there must be some hidden variables, some missing pieces of the puzzle that would explain this seemingly impossible connection.
Okay.
He and his colleagues even proposed a thought experiment known as the EPR paradox to challenge the whole idea.
And this is where the story gets really interesting, right?
Yeah.
Because later experiments actually proved Einstein wrong?
Exactly. The Oxford article dives into this in detail.
Okay.
It explains Bell's inequality,
Right.
a mathematical theorem
Uh-huh.
that essentially allows us to test whether those hidden variables Einstein was talking about
Yeah,
can explain the results of experiments with entangled particles.
I see.
And what's remarkable is that experiments have repeatedly shown that Bell's inequality is violated,
Wow.
which means hidden variables are out.
So spooky action at a distance is actually real.
Yeah.
This is blowing my mind. Imagine two particles. They're linked in a way that they share a single fate, like a single wave function. When you measure the state of one particle, say its spin, you instantly know the state of the other, even if they're light years apart. There are no hidden variables that can explain the correlations we see between entangled particles. They're genuinely linked in a way that goes beyond our usual ideas of space and time. Okay, my head's spinning a little here. So, what does this tell us about the speed of light? Are we really seeing information travel faster than light?
That's where it gets even more interesting. We can't actually control which state an entangled particle will collapse into when we measure it. It's random. So while there's this instant correlation, we can't use it to actually send a message faster than light.
So it's like a cosmic coincidence. We know they're connected, but we can't use it for anything.
Exactly. And that brings us back to what makes entanglement so profound. It suggests a deeper, non-local connection between particles, a connection that doesn't get weaker with distance. It challenges our very understanding of what it means to be separated in space and time.
So no quantum texting across the galaxy. Kind of disappointing, but also maybe a good thing. My brain is already hurting just thinking about these instant connections.
It's definitely a concept that pushes the limits of what we thought we knew about the universe. But even though we can't use entanglement for, faster than light messages, it still has some mind-blowing implications.
Okay, I'm ready to be blown away. What else does entanglement tell us about reality? Especially when it comes to how we think about space and time.
Well, it kind of throws a wrench in the idea that space and time are fundamental, independent things in the universe.
Okay, I'm following her so far.
Think about it. If two particles can be instantly connected no matter how far apart they are, what does that even mean for the idea of separation?
It's like they're not truly separated at all. Like maybe distance is just an illusion.
That's one way to look at it. Some physicists believe that entanglement is pointing to a deeper level of reality, one where everything is connected, a reality that goes beyond our everyday experience of space and time.
Whoa, that's getting pretty deep.
It is. It's like those particles are part of a single unified system, even when they look like they're light years apart.
So we're not just talking about tiny particles here, right? You mentioned earlier that entanglement might be involved in some pretty big mysteries, like black holes.
Yeah. There's more and more evidence that suggests entanglement could be key to understanding black holes. Those cosmic monsters that, warp space and time to the extreme.
Black holes, always a crowd pleaser.
Right. Some theories suggest that the information paradox...
What happens to information that falls into a black hole?
Exactly. That paradox might be solved by looking at the entanglement between particles inside and outside the black hole.
So even these massive objects, these things that seem to break the laws of physics, might actually be ruled by the same quantum principles that apply to tiny particles.
It's pretty amazing, right? And it might not stop at black holes.
Okay, there's more.
Some physicists even think that entanglement could play a role in the emergence of consciousness.
Whoa, hold on. Quantum consciousness, that sounds like a deep dive for another day.
Definitely. But it does raise some really interesting questions.
It does. It makes you wonder, where does the quantumness end and the everydayness begin? I mean, we're all made of these particles behaving in these bizarre ways. Why don't we see it on a larger scale?
That's the big question. Why does the quantum world, with its superpositions and entanglements, seem to fade away as things get bigger?
Yeah. Why don't we see cats or people, doing quantum things?
It's one of the biggest unsolved mysteries in physics.
So we've got these mind-blowing concepts that work perfectly at the subatomic level, but then they seem to disappear in our everyday world. Is there a point where quantum mechanics just stops working?
It's not so much that it stops working, it's more that the effects become incredibly difficult to detect.
Okay.
Some physicists think that interactions with the environment, all those constant measurements happening all around us, cause quantum systems to decohere, lose their quantumness.
And behave more like, well, normal stuff.
Right. Others think that gravity might have something to do with it, suppressing quantum effects at larger scales. It's an area where there's a lot of research happening, but no definite answers yet.
So the line between quantum and classical is more of a blurry zone than a hard line.
Exactly.
Yeah.
And that blurry zone is where some of the most exciting research is happening.
I bet.
By figuring out how quantum systems interact with their environment, we might finally figure out how the quantum world creates the classical world that we see and experience.
Okay, so we may not be teleporting through walls anytime soon.
Probably not.
But these concepts are still shaping our reality at the most fundamental level. It's like we're seeing the universe with new eyes.
Yeah.
Realizing that what we thought was solid and separate might actually be way more interconnected and, well, fluid than we ever imagined.
I like that, a fluid reality. And this new perspective, it has the potential to revolutionize not just how we understand the cosmos, but also our technological capabilities.
So we've got these mind-bending theoretical possibilities.
Right.
But how does any of this quantum weirdness actually show up in our everyday lives?
It's easy to think of quantum mechanics as this, really out there thing that only physicists and labs need to worry about.
Yeah.
But the truth is, it's, all around us.
Okay.
It underpins so much of modern technology.
Right.
From the smartphones in our pockets to medical imaging that saves lives.
So while we're debating whether our consciousness is creating reality, quantum mechanics is quietly powering
Yeah.
the devices we use every day.
Yeah.
That's kind of a wild thought.
It is, isn't it? Take semiconductors, for example. They're the
Okay.
heart of all our electronic devices.
Right.
And they rely on the quantum behavior of electrons.
Gotcha.
Without an understanding of quantum mechanics, we wouldn't have computers,
Wow.
smartphones, or the internet,
So our digital world is basically built on quantum principles.
pretty much.
What other examples come to mind?
Well, think about medical imaging,
Okay.
MRI machines, which allow doctors to see inside our bodies without surgery, use powerful magnets to manipulate the spins of atomic nuclei.
Okay.
This technology is based on the principles of nuclear magnetic resonance, which is a direct application of quantum mechanics.
Wow. So even saving lives is becoming increasingly dependent on
Yeah.
our understanding of the quantum world. It's incredible to think how far we've come. But it also makes me wonder, what the future holds.
Yeah.
What kind of technologies might be possible if we could unlock the secrets of quantum mechanics even further?
The possibilities are truly mind-boggling.
Yeah.
One area that holds immense potential is quantum computing.
Okay.
While classical computers rely on bits, which can be either a 0 or a 1,
Right.
quantum computers use qubits,
Okay.
which can be in a superposition of both states simultaneously.
I see.
This allows them to perform calculations exponentially faster than classical computers for certain types of problems.
So we're talking about solving problems that would take classical computers millions of years.
Yeah.
In a matter of hours or even minutes.
Exactly. Quantum computers have the potential to revolutionize fields,
Wow.
like drug discovery materials, science, and artificial intelligence.
Okay.
Imagine designing life-saving drugs with pinpoint accuracy,
Right.
creating entirely new materials with unheard of properties,
Gotcha.
or developing AI systems that can learn and adapt at an unprecedented rate.
It sounds like science fiction, but it's actually within reach.
I think so.
But what about this idea that our current tools are too crude for the quantum world?
Yeah.
Wouldn't that also limit our ability to develop these advanced technologies?
You're hitting on a crucial point.
Okay.
There's a constant interplay between our understanding of the quantum world
Right.
and our ability to create tools that allow us to explore it further.
Gotcha.
As we develop more sophisticated instruments, we uncover new mysteries and push the boundaries of what's possible even further.
It's a continuous cycle of discovery, innovation, and pushing the limits of human ingenuity.
Precisely, and that's what makes this field so incredibly exciting.
Yeah.
We're just beginning to scratch the surface of what's possible with quantum mechanics.
Okay.
The discoveries we make in the coming decades could fundamentally reshape our understanding of the universe and our place within it.
So after this deep dive into the quantum realm, what's the biggest takeaway for our listeners? What should they walk away pondering?
I think the most important takeaway is that reality is far stranger
Okay.
and more wondrous than we ever imagine.
Yeah.
The universe isn't just a collection of separate objects,
Right.
but a vast interconnected web of possibilities constantly in flux.
And the act of observation, whether by a conscious observer
Right.
or a scientific instrument, plays a crucial role in shaping the reality we perceive.
Absolutely. So the next time you look at the world around you, remember
Yeah.
that there's much more going on beneath the surface than meets the eye.
I like that.
There's a hidden realm of quantum strangeness
Okay.
where the rules of classical physics break down,
Right.
and the very nature of reality is still a mystery waiting to be unraveled.
That's a fantastic note to end on to all our listeners out there.
Yeah.
Keep asking questions, keep exploring, and never stop being curious about the universe
Right.
and all its mysteries.
Because who knows, the answers you find might just change the world.